I found a way to rest my foot and create videos, so we're going to see how this works. Today's video is all about section 7C, which is the law of large numbers. So what is the law of large numbers? The law of large numbers applies to a process for which the probability of an event A is P of A, and the results of repeated trials are independent. So if the process is repeated over and over again, what we expect to happen is the proportion of trials which A occurs should be closer to the probability P of A. What does that mean? Really, it means we have two kinds of probabilities we talked about in 7A. We have theoretical probability, which is what we expect to happen over time, and then we have empirical probability, which is what we observe happen in a specific experiment. So I'll give you a quick example before we go into the roulette example here. Suppose I have a coin and I were to flip it 10 times. If the coin is perfectly fair, what we would expect to happen is that we would get an equal distribution of heads and tails, 5 heads and 5 tails. Now, is that going to exactly happen if I flip a coin 10 times? No. I could actually get 3 heads and 7 tails, or I could get 1 head and 9 tails, or I could get 8 heads and 2 tails. I could get all sorts of different combinations, just kind of how the luck distributes those heads and tails. But what the law of large numbers tells us is that over time, when I increase the number of flips, that the proportion of heads and the proportion of tails should get closer and closer to 50%. So if I flip a coin 10 times, maybe I do get 5 and 5, or maybe I get 8 heads and 2 tails. But if I flip a coin 100 times, or 1,000 times, or 100,000 times, I expect those proportions to get closer and closer to 50%, which is the theoretical probability. So we'll look at this example here. We have a roulette wheel. It says a roulette wheel has 38 numbers, 18 of them are black, 18 are red, and then we have the numbers 0 and 00 that are in green. So we assume that all those outcomes are equally likely. We want to know what's the probability of getting a red number on any spin. And so remember, probability can be expressed in the numerator as the number of outcomes that satisfy what we're looking for, and the denominator being the total number of outcomes. In this problem, there were 18 reds out of 38 numbers total, and so the probability can be thought of as 18 over 38. I went ahead and expressed that as a decimal rounded to 3 decimal places, and it's 0.474. And so the part B asks us if patrons spin the wheel 100,000 times, about how many times should we expect to get a red number? Well, we can multiply 100,000 times that decimal value, or that ratio that we found earlier. And when we do that, 100,000 times 0.474, we end up finding out that in 100,000 trials, we can expect about 47,400 red values. Similarly, we should expect the same amount of black values because they have an equal distribution on the roulette wheel. The other, 5,200 of the 100,000 spins, we expect to land on either 0 or 00. Now, if I spin a wheel 100,000 times, is that going to be the distribution that happens? Maybe, maybe not. Most likely not exactly going to happen that way. But the more trials we do, the more likely we expect those values to get closer to the theoretical probability. So that leads us to the most important thing in the law of large numbers section, which is all about expected value. Expected value is really, really important in mathematics and probability, particularly in a place like Las Vegas, which is built on probability. What expected value does is it takes into combination two different things: the probability of an event happening, and then the risk or benefit monetarily of winning or losing. And so different games that we use in the casinos have different payouts, and those payouts are based on probabilities. When we take all the different probabilities and look at all the different possible payouts, what it does is it returns us a number that tells us how much we should be expected to win or lose every time we participate in that game. Obviously, it has really big implications for casino games. But there's more than just casino games where expected value comes into play. So the example that we're going to look at right here is all about automobile insurance. So it says, suppose an automobile insurance company sells a policy with an annual premium of $200. Based on data from past claims, the company has calculated the following probabilities. It tells you that 1 in 50 policyholders will file a claim of $2,000, 1 in 20 will file a claim of $1,000, 1 in 10 will file a claim of $500. So it says, assume the policyholder could file any of the claims above. What is the expected value to the company for each policy sold? So when we talk about expected value, it's also important for us to discuss who the expected value is for. We could actually calculate two expected values in this problem. We could calculate the expected value for the insurance company, which we assume is a positive number because the insurance company is making money over time. Or we could assign the expected value to the insurance purchaser or the customer. And in this specific example, we assume that the customer is actually going to lose a little bit of money over time by paying for insurance. That's part of the deal. You pay for insurance every month. Are you going to need it every month? No, probably not. But just in case you need it, you don't have to come out with $10,000 or $20,000 out of pocket, because that's why we pay for the insurance ahead of time. So with that in mind, let me flip my camera. Sorry. And we'll write out some important information about expected value. So, in terms of expected value, what do we need to know? Expected value can be calculated as gains times probability of gain minus losses times probability of losses. I like to put the probability in parentheses. Anything that's a gain to the company or to whoever we're calculating expected value for is going to be positive, and any losses that we have we're going to write out as negatives. So in this problem right here, the insurance company sells a policy with an annual premium of $200. The $200 that they charge right off the top is a gain to the insurance company. Whether you get in an accident or not, you have to pay that $200. The insurance company can guarantee that that money's coming in. The probability of you spending that $200 is 100% because everybody's got to pay for the insurance. So, expected value, which I'm going to now use EXP for. Expected value can be thought of as the gains. Again, this company, in order to get their insurance, you got to pay $200, and the probability that you're going to pay $200 is 100%. So I'm going to write that in as a 1. 100% as a decimal can be expressed as 1. Now, all of these claims that could possibly be filed, these are losses to the insurance company. Insurance company doesn't want you to get in an accident. They would be happy if you just paid your money and didn't have to worry about having to shell out for any accident-related stuff. Fix your car, go to the hospital and get your broken foot fixed or whatever. The insurance company doesn't want to do that, but they know that there is a chance, a good chance sometimes, that they are going to have to file claims. And so they put a probability associated to those claims so that they have an idea of how to assess the risk associated. That's also how they determine how much they should charge you for your premium. So let's write out all the losses and make sure when we write out these losses that each one of them is going to be negative. So what could we lose? If as an insurance company, we could lose $2,000, and we have a 1 in 50 chance of that happening. We could lose $1,000, and we have a 1 in 20 chance of that happening. Or we could lose $500. We have a 1 in 10 chance of that happening. Remember, order of operations tells us to take care of the multiplication first. So let's write all these out. Again, the gain to the insurance company, $200 for every policyholder. $2,000 times 1 over 50 is 40. 1,000 times 1 over 20 is 50. And 500 times 1 over 10 is also 50. When we combined all these, we get 200 minus 140, which is $60. This is the expected value to the insurance company. In other words, what we expect is that for each person that the insurance company is able to sell a policy to, the insurance company should expect to make $60 for each policy that is sold. Oftentimes a follow-up question is, if I sold 10,000 policies, what can I expect the total value to be, or the total gain to the company? The more you sell, the more you're going to have an expected value. It's simply just taking that expected value and multiplying by the number of participants or the number of trials. So this problem is telling us we expect the insurance company to make $60 per policyholder. The last important concept in law of large numbers that you could see is called the house edge. House edge is just another way of saying expected value to the game maker itself. So house edge is just saying expected value to the casino, if you will. Remember, all those casino games that are built on the strip are designed to make money. So the expected value to the casino should be positive, and the expected value to the player should be negative. A very good casino game is going to have a very small expected value. And the reason why is because people that are playing those games want to feel like they have a good chance of winning. If you make the expected value so large, people are not going to be interested in playing that game because they're not going to feel like they win. So you want to make that expected value very close to zero, but very positive, so that over and over as time goes on, the game continues to make money. It may be a small amount of money, cents for every time you play, but if people are playing 1,000 times and you have 1,000 people that are playing that game, you can see that 1,000,000 trials is not something that's going to take a very long period of time. So that's everything in section 6C. Section 7C. The next video will talk to you all about mini project 7 and also big project 3, which is going to ask you to build your own game and calculate its expected value. One more thing though before we go, I'd like to do one more example from my math lab. So on your own, here's a problem. This would have been like a warm-up in class. But you can give yourself a minute, you can look at it, you can work on it, pause the video if you like, and then we'll run through it as well. It says an insurance policy sells for $600. Again, that's going to be a gain to the insurance company. And then it says an average of 1 out of 125 policyholders will file a $15,000 claim. Oh, actually, let's put our fraction next to 600, which is 1, because everybody has to pay for that insurance. Then it also tells us an average of 1 in 200 policyholders will file a $50,000 claim. And 1 in 500 policyholders will file a $70,000 claim. And we want to calculate the expected value. Remember that this value over here, this value over here is the gains. And all of these ones that I have made negative are potential losses to the insurance company. Then we calculate. The gains, of course, is 600. They get 600 off the top from everybody. And then as we multiply these through, we get 120, we get 250, and then lastly 140. This is 600 minus 510, which is an average or a total value of $90 per policyholder. So our expected value is 90 bucks. Like I mentioned, usually there's a follow-up question. In this one, it says if the company sells 20,000 policies, if they sell 20,000 policies, what's the expected profit or loss? Remember that this value is positive, and so this is a profit to the insurance company. So if they sell 20,000 policies, we're going to take our 90 bucks, we're going to multiply it by 20,000, and we get $1.8 million. So we expect a profit of $1,800,000. In our next video, I'll give you another example of that just to make sure that you feel good about it. We'll go through the law of large numbers mini project, and I'll also talk to you about big project 3, which is all about creating a game. Have a great day.